everyone, and welcome to another episode of the Data Science Decoded podcast. I am here with Mike and Nir. How are you guys?
I'm okay. By the way, if Daniel maybe forgot, we just reached 1,000 subscribers on YouTube, and I think
the happy dance.
yeah, and now it is about 1,060, so it keeps growing, and I think it is a quite piece of achievement because we started from nothing. I think in the end of July, and we got to 1,000 subscribers in 4.5 months. And our podcast is not about very simple stuff, and our audience is not very wide. So I think we can write ourselves. We can write it down as quite a big achievement. At least for me, in my head, it is quite a big achievement.
Good point. Thank you, and thanks to you, the audience as well, that listening. We appreciate it.
And keeps us subscribing.
Yeah. Absolutely.
And how are you, Nir?
Doing good. Thank you.
Is it a little bit chilly? I see the
it's chill. I mean, let's say 15 Celsius, something like that.
Yeah.
Not it's not freezing. The sun is still shining here, and the skies are blue. It's just the temperature is a little bit less than what we are accustomed to in the summer, but it's not snowing out there.
Is it raining in our location, by the way?
No. It's kind of the weather reminds me of Israel. So think about Israel in the desert. That's the same weather type.
Oh.
By the way, I also use hats in the winter, like an umbrella.
Nice.
Yeah. It's multifunctional.
So I'm only the only one who is not using it. I'm using umbrellas. But I'm trying to.
They always break
when it is raining, because I quite hate rains. Yeah.
Okay, so let's begin the review of the paper of what we're doing today. And as you can see, it's called the Monte Carlo method. I guess many of our listeners are familiar with it. I also encounter it in my in the past, but I never went over the paper. So it's from 1949 by Nicholas Metropolis and S. Ulam. I don't know what the S stands for. Let's see here. If it says, no. Still, just S. Okay. But I know that both were at Los Alamos, right? So they were working on the nuclear bomb. And it was interesting paper in a sense that many words, but not a lot of math, right, guys? So not your type of paper.
Yeah, but compared to other papers without almost any equations, this paper is actually very deep, because the idea introduced in this paper was quite novel 80 years ago, and this is just an impressive idea,
Yeah, definitely.
So it was published in the Journal of the American Statistical Association. So it's a strong journal. And I'll read the abstract. It says, we shall present here the motivation and general description of a method dealing with a class of problems in mathematical physics. The method is essentially a statistical approach to the study of differential equations, or more generally of integral differential equations that occur in various branches of natural sciences. Okay, so that sounds general. And the idea here, as far as I can tell, is to leverage computation, right? So it's 1949, and they're working on a nuclear bomb, and I think they are doing practical stuff, right? They don't have time now to derive various convergent theorems and stuff. So I think they found the method that works and then gave some motivation. That's as far as I can tell. The background.
This is by the way called an applied mathematics compared to the pure mathematics in which you have these convergence theorems and stuff like that. By the way, pure mathematics is as important as an applied one. So, but this paper belongs to the applied mathematics, and here he's talking about differential equations or integral differential equations. But actually, the applications of Monte Carlo are much more broad now. You can find it in an enormous number of branches of mathematics and physics and data science. It is almost unlimited the number of applications of this method.
Definitely, yeah. Biology, physics, even economy.
Economy, yeah.
It's everywhere. Yeah.
So, Mike, to our listeners that are not familiar with the Monte Carlo, can you give a few sentences on how it works? Like, what do you do with it? If you wanna, high level.
Yeah, in a very high level, MSU may have a very complex problem. You know, for example, you need to measure some area which is defined by the very complex mathematical equation, really very complex. For example, one of the very good examples of using Monte Carlo method is measuring the square of so-called Mandelbrot area. Mandelbrot area, which is very complex area, which is an area of some iterative complex valued equation. You just can't compute it analytically, and then what can you do? But this area is limited, say, by some square with some side of, let's say, x. Okay, so what you're doing, you are just sampling your points inside this square, and then the points, and you have an ability to measure whether this point falls into this area, into this Mandelbrot area or different area, and then you just measure which portion of the points fell into this area, and then you just take this portion and you just multiply it by the square of this square, which is in which this area is enclosed, and then you get it depends on the number of points you are sampling. You get a quite good estimate of the area of this area, for example, Mandelbrot area, which is defined, as I already said, by very complex iterative equations. And by the way, there are some method. The similar method can be used to compute pi. Mm-hmm. You know, we know that the area of the, how is it? I forgot the word in English.
Circumference? Circle? Okay. Circle.
I don't remember. I forgot it all. The circle area.
I thought you forgot circumference, but you forgot circle.
No. The circle area is just the radius equals to 1 is pi. And then you can put it in some square on the other side, for example, 1, and then you can just sample your points inside this square, and then you can compute the number of points which fell into this circle, and you get a very good estimate of pi. By the way, it is a square of the side of 2, right? Yes, because we have a radius equal to 1.
Of 1, yeah.
Yes.
Yeah, this specific experiment is actually something that I put in my book on the chapter of Monte Carlo. So, and just for the listeners to know, Monte Carlo
is which book? Tell us about it.
My book is called understanding probability with Python, and the one that wrote the reference for this book is actually Mike.
Yeah,
So
I
so
admit.
yeah, I was fortunate and grateful for Mike writing this dedication to my book, and chapter 9 is the Monte Carlo simulation. That's the chapter on Monte Carlo simulation, and there I also show how to do this exact estimating pi type of experiment. And I don't know if you guys know, but Monte Carlo is a casino, right?
Exactly.
Yeah.
In Monaco, I think.
Yeah. I think in
Location,
Monaco.
France, yeah. There's many
Yeah.
casinos.
Yes. And it's basically, I think about Monte Carlo as, for some reason we can't solve something analytically. Let's say, or for example, the probabilistic problem that we're facing has too many outcomes, too many possible outcomes to actually solve it on paper, so to speak. So we're going to simulate, instead of solving, we're going to simulate just a portion of that and use the law of large numbers to say, okay, the relative frequency or the ratio will estimate the actual probability or probabilities.
Perfect.
And
So I know what to ask for my birthday. Your book, Nir,
okay, yeah, sure.
as a present.
Absolutely, yeah.
Amazing.
You have printed version?
I haven't printed it. People are buying it on my website online because it's a book with a lot of code. But I have the PDF. I mean, I can definitely, whenever I want, I can publish it on platforms like Amazon. But I haven't done it yet, unfortunately, because not because I don't want to, but because I don't have the time right now. So
Yeah. So guys, if we look at the paper, so there, I think there's 4 chapters, and here on the first chapter, the example they give is similar to what you said. So they say, consider the problem of evaluating the volume of a region. So again, calculate the area or volume in a 20-dimensional space. Okay, so there are 20 dimensions. And the region of interest is defined by, some function of which is this 20-dimensional space between x1 to x20. And there's many constraints. So for example, just to the listeners, let's say if I want to calculate the area of a circle, like Mike was talking, so I need to write the equation of a circle and then make it be smaller than 1, right, if the radius is 1. So here they calculate not a circle, but some kind of area in 20-dimensional space. So there's some general function with 20 variables. And they say, okay, if you want to do it numerically and do all the calculations, it's going to be plenty of calculation, right? Depends on how you discretize each dimension. And instead, you can just do sampling, right? And they say, here again, the more sensible approach would be to take, say, 10 to the power of 4 points at random from the ensemble and examine those only. Yep. Okay, and they say we should count how many of the selected points satisfy all the inequalities, meaning they fall inside this area. Yeah. And it follows from simple application of ergodic theorems that the estimate should be, with great probability, valid within a few percent. So you can tell that they're probably physicists, right? Because there's like hand waving here. And they do like a name dropping. Because of ergodic theorems, so that's why it works. Which I'll add just It's correct. I know. It reminds me of our first episode we discussed for, I think, or maybe the Shannon one. We discussed a few minutes ergodic theorem. How are you connected here, Mike?
I wanted to remark not about how this is connected,
Okay.
I wanted to ask, because there are several ergodic theorems, and here the main convergence of the Monte Carlo sampling of the Monte Carlo method, it follows from the law of large numbers. I think it follows even from the weak law of the large numbers, and the convergence rate, I think it follows from the central limit theorem. And it is interesting if these theorems, the weak law of the large numbers and the central limit theorem, can we call them ergodic theorems? I'm not sure. Maybe there are some theorems which we are not aware of, but for the best
I'll
of my
tell you how I understood it.
Okay.
Why ergodic? Because you sample randomly. So you assume like a uniform distribution, and you sample. And I think ergodic process gives you the ability to say it doesn't matter who's first and who's second, right? And or something like that. So like the order of sampling that doesn't really matter. It's like the example that I give with coins. It's, let's say you have 100 coins, you can flip them all at once, get some results, or take one coin and flip it 100 times. If it's ergodic, you should get the same result. So it's similar. Neil.
For us engineers, the way that we are studying ergodicity is we're observing a process in time, through time. It's exactly what you said, Daniel, through time. And he gives examples down in the paper from nuclear stuff that reproduces through time until the energy is decaying to a threshold that is undetectable. But this, in order for us to be 100%, quote unquote, sure that we can use the same distribution law for a process of t equals 1 and t equals 10 seconds, for example, we need to invoke ergodicity. Otherwise, the probability distribution can change through time. And that's I think that's why he mentioned it here. That's what I understand. But maybe he thought about something else completely. I don't know.
Yeah, they don't give formulations.
But by the way, I just started to think ergodicity and stationarity. Stationarity is talking about some autocorrelation, which does not depend on time, and ergodicity is about the probability, the distribution itself. What is the difference? Because
ergodicity is saying, stationarity is saying that the first moment is constant through time, and the second moment, and the second, that's the weak stationarity, and the second moment is the autocorrelation function is a function of only the time difference.
Okay,
exactly.
That's a stationarity. The ergodicity is saying that taking the sample mean over the ensemble equals to taking the sample mean over time, and it's not the same thing usually.
Interesting.
So, in other words, drawing 1,000 points, let's say from a distribution in time t equals 0, and taking the mean is we'll get the same answer as drawing 10 points for t equals 0, 10 points for t equals 1, 100 times like that, and taking the mean, which is not trivial at all.
The distribution function just doesn't depend on t, right?
Exactly. Something. So this is the first moment type of ergodicity, and this is like a weaker type of ergodicity. I think it's also relevant for Monte Carlo because over there we're taking means and proportions, right?
Yeah.
And I think that's why he invokes it here. We use it. This assumption is used in all applied mathematics applications in which time is changing when we're sampling processes.
Yeah.
Cool. By the way, it's funny, something I forgot to say, they never explain why they call it Monte Carlo in the paper itself.
No.
Like they just throw the Monte here. It's referred here as the Monte Carlo method. In retrospect, we know like the stories, but they didn't say it in the paper.
Yeah.
I'll continue. There were a few important points I wanted to show. Here, chapter number 3, they say we want now to point out that modern computing machines are extremely well suited to perform the procedures described. Okay, so again.
Yeah, and then he describes cards with alls and punches, you know, like the horror stories we hear from our fathers and grandfathers. So
Yeah. Exactly.
Yeah, and he described here how with computers you can generate any distribution that you want by starting with with a uniform distribution.
Yeah.
And then you can, which a uniform distribution you can do like pseudo randomly on a computer, and then apply like a G, which is general function on the output, and if you want whatever G, you can get it.
Yeah. But by the way, interestingly enough, usually it's not needed. Usually in Monte Carlo problems, all that we need is the mean, is the expected value estimation, which is the sample mean. And we use also in machine learning, by the way, we use always the convenient way in probability of estimating the mean of a derived random variable, which is to use the first probability, the original probability distribution in the integral, but inject into the integral the g of x instead of x, and that will calculate the mean of g of x actually, without calculating the actual distribution function of g of x. So that's something that is very nice, and that's what we use in Monte Carlo simulation to estimate integrals, right?
Yeah. By the way,
no one add. Oh, so you first, Mike, and then I'll add something.
Just a couple of small remarks. The first one is that these times, at least according to what I've read on the internet, you were not generating random numbers by some Python code. You used to have books which contain these random numbers. Just imagine it. You don't run numpy.random. You know what? You just got to use some books in which these random numbers appear. Okay, and now it sounds crazy, but at least according to what I read, this was a situation. And by the way, my second remark, in many situations, we just can't. We want to evaluate some function, some distribution, but we can't straightforwardly sample from this distribution. And after Monte Carlo came the method which are called the rejection sampling and the importance sampling. So we are not sampling from the target distribution on which we want to compute some expectation of something, but we sample from some more convenient distribution, and they're making some mathematical computation in order to build the estimate of it. So this method of Monte Carlo shaped a whole family of methods which allowed us even not to sample from the distribution of interest. And for me, it was very interesting to learn it, 25 years ago.
Yeah.
So that was cool, and we'll see it in the future. We're gonna go over those papers.
Yeah.
Are you guys in your field, like in your jobs, are you guys using Monte Carlo for anything?
I'm not using.
Okay, so for example, I use it a lot for radar simulation, stuff like that. every LiDAR simulation, every system, we can simulate it completely with Monte Carlo, end to end. So, adding noise, SNRs, all these are Monte Carlo type simulations. Performance of detectors, we can evaluate it in a Monte Carlo simulation without any hardware. Before we even start designing the hardware, we can simulate the physical environment and pass the particles, so to speak, through all of these constraints or the equations.
Interesting.
And I think that's what they are saying here. By the way, I also treat all the field or the concept of, in data science, machine learning, all the concept of data augmentation. For me, it's adding more random points like Monte Carlo. Because sometimes in my field, at least, we augment data by adding noise to it in different levels of noise, like different SNRs. Okay.
I'm trying to think how it's connected to data augmentation.
Because I generate a lot of new points from a statistical distribution. For example, take an image.
But also bootstrapping, you generate points from data. But the difference is, in bootstrapping, you have already data and you do stuff with it.
Yes.
Here you don't have data. You have the other. Here it's like the other way around. You have the theoretical assumption, and from the assumption you generate data, not the other.
Right. But think of it like that. Maybe we have data from some source. We don't know the source. Okay, we don't know the probability distribution function, and this data is not enough for us to build a model that will generalize well. Okay, so what do? We augment the data. How?
That's true.
Maybe we randomize it a little bit. Okay, shift it, scale it, whatever. Add noise to it, different kind of noises, different kind of stochastic processes on it, and now we have a lot of more data that we can work with that were generated completely randomly, and that we kind of like forced drawing from a distribution of sorts. And I see it as a Monte Carlo method, even though it's not specifically meant for that. But that's the way I interpreted it, at least.
Conceptually, I think it is kind of close. And then I think about the Monte Carlo method in machine learning and the stuff we are doing every day. Just talk about cross-validation. Then I want to assess my model performance. I do numerous splits of my data set onto train and test.
Yes.
And then I train on the train set and evaluate on the test on the test set. And then I build some curve which measures the performance of my model on different test sets. It is not a pure Monte Carlo, but still, at least in my head, it is somehow related. This is
okay. I see. I see why, because I think on this similar, because to me, like, Monte Carlo is simulating different worlds, right? And like every outcome of the Monte Carlo is like a different world that is possible, and then you calculate whatever. And similar you do with like cross-validation, right? You try to simulate like a specific world, and then you like average them. So maybe that's how I agree with you, Mike.
Yeah, but by the way, I'm not sure it is somehow related. But then you when you're generating your data with the diffusion models, score-based models, you have your data, and then you start from training your model to generate very noise data. You add some noise to your data, and then you train your model to generate this noisy data, and then you gradually reduce the amount of noise you're adding to the data, and in the results at the end you get the pure data, pure data without or with a very small amount of noise. It is not Monte Carlo, but you still, you are playing with adding some noise and sampling. This idea of playing with the sampling for different purposes, this idea is impressive. I think it is one of the biggest ideas of the 20th century in the mathematics. I think one of the 10 most powerful ideas of the 20th century math.
Yes,
For me,
yes, yes. By the way, question, Mike, Daniel, to both of you, GANs, not guns, GANs. We start with it's basically we're injecting noise, right, into the system, and the system learns, so to speak, quote unquote, learns the underlying probability distribution function and spitting out, if it's trained well, spitting out something that makes sense, right, or that looks real in the GAN world. Does this?
What is the question?
The question is, how does this relate in your minds to Monte Carlo? Because we are generating a lot of random points for that, for the start, right?
Yeah, I'm not sure, because again, to me, Monte Carlo is you have some kind of, you start with a formula, so you have assumption on the distribution function, but maybe there is also with
We have the formula.
guns.
The formula is discriminate. That's how I think about it.
Yeah, he tries to learn this. Yeah, that's an interesting question.
I'm not sure I have a good answer for you on this question, because you're trying to generate data from noise, but how is it related, and if whether it is related to the Monte Carlo, I need to think about it.
Okay. Hey guys, I have a book recommendation about these methods.
Perfect. Another birthday present.
No, that's not.
I'm just kidding.
My book. This is the book. The book is called
Simulation.
By Sheldon M. Ross. I have the 5th edition, and this will cover everything you need to know about Monte Carlo and other stuff, like Mike mentioned, importance sampling and rejection sampling, and a lot more.
Cool. I just wanted to add something before I forget. They say here, the statistical methods can be applied by many computers working in parallel and independently. Okay, so that's an important point. Again, to us, it's self-obvious, right? That you can parallelize stuff, but to them it was amazing. Oh my God, we can save time. So that's really cool. At least when I was reading it.
Long before the GPU era.
Yeah, and and here, like, there's another chapter. I feel like every chapter they do the same thing, but give a different example of how to use it. I'll just go to the end and read what they say. The asymptotic theorems so far established provide the analogous of the laws of large numbers, such as the generalization of the weak and strong theorems of Bernoulli, Cantelli-Borel. Again, I'm not a mathematician. I'm not sure what does it mean. Maybe you explain soon, Mike. And I'll just finish. The more precise information corresponding to that given in the Laplace-Lyapunov theory of additive processes has not yet been obtained for our more general case. In particular, it seems very difficult to estimate in a precise fashion the probability of the error due to the finiteness of the sample. This estimate would be of great practical importance, since it alone would allow us to suit the size of the sample to the desired accuracy. You wanted to say something, Mike?
I'm not sure. I have much to say, because I forgot to check what is Cantelli-Borel theorem. It is quite famous theorem, and 15 years ago, 20 years ago, when I was doing my PhD, I knew it for sure, but I just forgot. But here, I think we are talking about convergence rates of different limit theorems, like weak law of large numbers and the strong law of large numbers, and of a central limit theorem. And we have similar theorems for random variables and random processes, which is distributed I forgot IID, not identically distributed,
independently.
independently identical distributed.
Distributed, yeah.
There are some theorems also about it. As for Laplace-Lyapunov theorem, I know it is Laplace transform. I know it is Lyapunov function, but I don't know this in the conjunction. I can't combine these two things which I know about Laplace and Lyapunov in Laplace-Lyapunov something. But I think he's talking about estimating or the precision of this estimate. There are sampling.
Yeah, exactly.
And they are trying to estimate with some quantity which we can hardly measure with some function of these samples. And he's talking about that is quite difficult to establish some theorems which actually give some convergence rate or some estimation error. I think he's talking about it.
You're right.
I'm not sure. Maybe they have some theorems about this convergence of Monte Carlo estimates. We need to check, but I think 80 years ago, I think it was the situation.
Yeah, we usually, as you said before, Mike, we usually do it in like the central limit theorem will secure the convergence and the convergence rate. It's like the sigma over sigma of the function of inside. You plug in all the random realizations over the square root of n or something like that, right? And as you increase n, you're more accurate, and you can do some sort of a confidence interval if you want. That's what we do in when we simulate radar stuff, at least.
Yeah, maybe it can be that quite tough math is involved here in the computing this estimate with these estimates.
Cool. Perfect. So we are at the end of the paper. I think we recommend to our readers to go over it. It's quite a fast read. I think you can read it end to end in 20 minutes, guys. Right? Makes sense.
Yeah.
And
not if you don't try to understand every equation, because you have some Schrödinger equation. If somebody doesn't know what is Schrödinger equation and wants to learn it, it can take some time. And there are some more equations. But if you not delve too deep in this equation, this paper is a quite easy read. And the idea of this paper is so brilliant. So you don't need to dive into all these equations.
Right.
Mm-hmm. Yeah, that's correct. Cool. So thank you, Mike. Thank you, Nir. Thank you, audience. And we're going to see you next time.
Thank you, guys. Bye-bye.
Thank you, guys. Bye-bye.
Bye.